All right, folks, a very warm welcome to Support Vectors, Research and Training Lab in AI. Right. It's going to be a little bit of a long session, but it will be very conversational today. And this is actually what I call precursor to RAG and AI Search Bootcamp, which is a little bit more technical. I'm reminded of the story. I always start with the story uh, of the devil. So one fine day, a person dies, and he has done equal parts good and evil, and they're not able to decide whether to send him to heaven or hell. So they say, "Why don't you choose?" He goes to heaven and says, "People are doing some bhajan or praise of God in songs and so forth." So then he goes to hell and he finds very interesting people, excellent coffee, good cookies, right? And then he makes up his mind and he says, "Well, this is where I want to be." And then he goes back to hell, and the devil is waiting there with a stick. And even the coffee is cold. So think of this as the orientation day in hell that looks good. I'm kidding. So, so in other words, today I'm going to introduce the whole subject of RAG and AI search in a very general way today and the next session. But the actual, while I'm joking about it, the actual session, which is the RAG and AI search bootcamp, tends to be far more elaborate and much more technical. The goal there is, in that particular course, is to teach you the kind of techniques that, frankly, are not talked about on the internet, that are only culled from deep experience of creating large-scale enterprise RAG systems, learning things the hard way, and validating it, and making sure that we are able to create high-performance RAG systems. And so that particular bootcamp is literally us sharing our knowledge, our experience in a format that is a course. Now I'm going to start with the main course. So today there'll be a discussion, right? I'll talk very broadly about RAG and AI search. Then I will show you in code, but I'll just walk you through the code. I'll show you the magic of RAG and AI search, but you won't have to necessarily do it yourself. Nevertheless, this GitHub is public. I'll show you the GitHub. We'll work you through the steps for Wednesday. We hope that if you're familiar with programming at all, then you have some basic environment set up so that when we meet on Wednesday, we can make a little bit more rapid progress. So this field, this topic, which is called, which I provocatively call RAG to riches. The title is provocative, of course, for a reason. It's a phrase in English language, rag to riches. There are all sorts of stories in Hollywood of somebody working hard and making his way or her way in life from rags, from humble beginnings, and so forth. But the reason I gave this provocative title is quite interesting. Today, RAG is the poster child of generative AI. If you ask what is one application of generative AI that nobody questions, it is worth it, that nobody says that it's hype, then most people would point to RAG, Retrieval Augmented Generation. If you look at ChatGPT, for example, which sort of had a huge impact in November 2022, if you remember the first time you encountered ChatGPT, it felt like magic, isn't it? Now today it has evolved into a RAG application. It's an agentic RAG system. When you engage with it, it searches the web if needed, isn't it, as a search index. It does things about it and use a multi-step process to answer your question. How many of you have not observed that about your questions that you ask in ChatGPT or Perplexity and so forth? So all of these things, whether you look at Google as a search engine itself, nowadays, when you search for something, do you notice that there's an explanation that pops up at the top? Google search has become RAG. Perplexity is, of course, the poster child of RAG, right? Agentic RAG. And all enterprises used to have a search system. It is inarguably a force for the good to transition from just search to retrieval augmented generation, right? If done well. So that is the point of RAG. And that is why the provocative title, Rag to Riches. But just like the gold rush of California many, many years ago, if you remember, and I often give this parallel, RAG is one technology that looks deceptively simple. Just like in the history here of California, people in the US thought all they have to do is start heading west. And if they head west and they hit California, sure enough, all they have to do is when they hit California, start digging. There will be gold. Reality was not so simple. It was far harder to find gold. The gold was there, but it was far harder to find it and mine it. Most of the great gold mines were taken up, right? And ordinary, you and me, the peasants, had a bit of a harder time finding gold. In a very similar way, today, RAG is something that is deceptively simple. How hard can it be? Take search results, feed it into a language model. You'll get some response. And there are all these libraries out there, so many libraries, open source libraries, that make it look as though it is just 3 lines of code. Right? For no particular reason, I will take one of the most popular libraries that I like, Llama Index. If you go and look at the tutorial, getting started with RAG, it's literally 3 lines. And so you may be persuaded that you just learned RAG. What was the big deal? Right? It's somewhat like heading west. To find gold, all we have to do is head west to California. But it doesn't quite work. As you will see, RAG is actually deceptively simple, but extraordinarily hard to get right. Why it is so is something that will form the context of the latter part of today. But before I get into what makes it hard and the technical aspects of RAG, and when I explain it to you, it will become dead obvious to you. But for 15 minutes, just humor me, because I would like to step back and take a more broad historical perspective, which is a bit atypical in our field. We are technical, we are all engineers. And we tend to, the first question we want to ask is, okay, what is my import statement? Import what and how do I start? Right? But I'd like to step back a little bit and take a more historical perspective or a civilizational perspective, because I feel that the importance of search and the importance of RAG transcends much of what we think we are doing in our enterprises, in our corporate environment. See, I always like to point out that if you look at humanity, human beings, Homo sapiens, we are actually pretty defenseless as a species. I go hiking every morning, very early when it's still dark. I go on a particular trail by a river, forested river, and it hits the bay. Right? It's hard to believe, but within Silicon Valley, there are still forested trails that go to the bay. So when I do go, it's the coyote season. And literally, I walk around the Coyote Hills. Right? You know why they're called Coyote Hills when you hike at the time that I hike, when it's still dark. There are coyotes around, and there are bobcats, and there are raptors, right? And then there are snakes. Right? All of those are there. Right? So when you are there, one of the realizations that dawns on you, and of course, when the fire season comes, then mountain lions show up. Very, very rarely, but because their habitat gets disturbed and they show up. And one of the realizations that I have practically every morning, because I encounter coyotes every morning, almost every day on my hike, is that how defenseless we are as a species. We have no claws, we have no fangs, right? We literally don't, right? Nevertheless, we are the most, in a way, arguably, the most successful, maybe the most troublesome too, but certainly the most successful species on this planet. So what accounts for us success, despite being essentially naked apes, defenseless, no claws, no fangs, right? How is it that as a species, the Homo sapien has survived so well? If you reflect upon it a little bit, there are many perspective or lenses through which you can look at it. But the one lens that I like to look at it is because in the Homo sapiens, there is a tradition of carrying the experience of one generation and passing it to the next. With animals, whatever gets baked into the DNA, into the instinct, gets transmitted. But with Homo sapiens, we pass our knowledge, we talk, we tell our children, we teach them. There is a body of knowledge that propagates forward. And that helps the children not have to go fight a tiger to learn how to fight a tiger, right? Or how to avoid a tiger, and how to survive, or how to build a house, or how to cook. It gets transmitted through experience. Through it's a shared experience, shared tradition that we carry forward. But part of knowledge is knowledge tends to have exponential growth. To give you a perspective of how knowledge grows, whatever mankind has discovered till today, as of this date, more knowledge, believe it or not, more knowledge will be discovered in the next 2 years. Right? That's the doubling rate of knowledge, the exponential growth. So when knowledge grows, it's like books. You start with one book, in the house, where's the book? If that book is short, you even remember which chapter has the answer to a question. Right? But as more and more books grow into your home, it becomes a little bit hard to remember what is where. Or where is the book at all? You go into a library, you would realize that the first thing you need is the Dewey system of indexing the books. Otherwise, despite a very vast and rich library, you would be unable to find the answers to the questions you're seeking. So indexing of that knowledge makes searching of precise information possible. And thus, to the extent that knowledge has been sort of a hallmark of our civilization, so has been the search of that knowledge and the libraries of knowledge. There is a lot about the Alexandria, the Library of Alexandria in Egypt, which people often trace, rightly or wrongly, that the decline of an entire civilization was tied to the burning or disappearance or neglect of the Library of Alexandria. In the Library of Alexandria was accumulated all the vast knowledge of mankind through great effort. And for a long time, the ancient civilization was flourishing. And with the decline of the Library of Alexandria, you can literally see the medieval ages, the beginnings of the medieval ages start, the Dark Ages start. And thus the relationship between knowledge, searchable knowledge, and human civilization. So search is foundational. If you look through this lens, ability to search is foundational. Is there anybody who can say they have been without Googling something for a whole week? It's second nature for us to go search for it in the digital. As knowledge has become digital, we Google it up. Right? So when we Google it up, the way that we look up at knowledge in a simple way used to be called keyword search in very simple terms. So I tend to just draw things out. So if you will humor me, I'll just draw these things out. So the traditional way that we used to do searches, suppose you had a thing like the cow jumped over the moon. Imagine that we have a document D1 and a document D2, another document which said Apollo 11 landed on the moon, right? And D3 is the cow was in the meadow. And I'll just take these three statements and so forth. In a very simple term, what you would do, or what traditional search engines are, and it has been there till 2018. And obviously, I'm giving you the kernel of the idea. Search engines by 2018 were industrial products. Google was very successful, right? Nevertheless, if you look at the kernel of the idea, how does it all work? It was quite actually simple. What you would do is you would look at the keyword and land, and you would create a dictionary of sorts. And in the dictionary, you would say cow is the keyword. And now which documents contain it? D1 contains it, and D3 contains it. Apollo 11 happens to be D2. Land happens to be D2, and moon happens to be D1, D2, and meadow happens to be D3. Okay? Very simplified. And this is what you call a search index. Sort of. Google had this at a ginormous scale. Now, suppose some user came and said, Apollo 11. So it makes sense that you would produce D2 as a document. If the user came and asked for the cow, now you had a bit of a problem. Two documents have cow, D1 and D3, right? And the second part of the search industry or in the information retrieval is what is the order in which you serve this? What is the ranking of the document? Relevance order of the document, of the search results, or the documents, right? So there were just two parts of this. Now, to compute the relevance, there were all sorts of algorithms like TF-IDF and BM25 and so forth. There's a whole search industry that addresses it. Suffice is to say that within the context of an inverted search, they really did an amazing job. They did many things, PageRank, this, that. They had ways to produce the most relevant documents for you. So this was the keyword search engine. And again, just to give you a basic sense of the history, this keyword search engine, and I'll keep it brief, and then we'll get into the thing. This is the keyword-based search engine, a search engine, or this is the search index, and associated with it would be the engine, the search engine that you do. Now, these search engines are today in modern language, people often call it the sparse indexing. The indexing that you see, they tend to call it sparse indexing for a variety of reasons. We'll come to it. And I'm being deliberately, technically, a little bit sloppy to get the main ideas across. And when you use Lucene, you don't typically use directly Lucene, but most of you have within your corporate environments, Elasticsearch, OpenSearch, Solr. Do those words look familiar, guys? Right? So that is what they are. They are essentially search indices of this kind with all of these relevance layer on top of it. So then came, and just to complete the history, something really big in 2018. So the watershed movement, and that you can say started all of this that we are talking about. It started with, and you will see the impact of it when I show you the Jupyter notebooks, the code. You'll see what a dramatic impact it has, but a little bit of a high level story. This year is sort of the watershed moment in the search industry. And this is fairly recent. There was a landmark paper that came out in June 2017, which has become pretty like perhaps the most celebrated paper in artificial intelligence. As many of you may have guessed its name, it's a attention is all you need. Exactly. Attention is all you need. And just a little bit, very short 30-second history about this paper. It came out of Google, and it introduced a creature, a very interesting neural creature called Transformer, a neural architecture with the name Transformer. So the moment you think Transformer, it brings to you the movies about the Transformers into your mind, right? So, or if you're an electrical engineer, you start thinking of power transformers, but it's neither of the two. But nevertheless, very powerful. And the title is provocative. Attention is all you need. What Google was trying to do, and I'll give you a bit of history. They were in the business of search and translation and so forth. At that time, there was a dominant neural architecture called, I mean, just mention the name, but if it doesn't ring a bell, it doesn't matter, called the recurrent neural networks. The recurrent neural networks, they had this property that you could feed it a sequence of words and it would come up. There used to be something called a language. They would build something called a language model, and this language model is something, it is important. And let me just say, you had an encoder and you had a decoder. So this is the part that we will focus on today to understand search. Suppose you have a text, the cow jumped over the moon. The moon. And I say, you give it to an encoder. The job of the encoder is, it's something like that. See, suppose I were to go today to Shanghai. I barely mastered a vocabulary of 400-500 words at this moment, right? All of a sudden, the need to master Chinese more globally has arisen quite recently. All of us are trying to, I suppose, master it. Right? So you have a certain vocabulary and you hear something and I hear something. Gradually, I parse it. And what do? My basic tendency would be to create a private representation, take out my diary and write it down in English or my native tongue. Right? And maybe in Chinese, what was said is, the cow jumped over the moon. Right? And I'll write it down, the cow jumped over the moon. And then if somebody asks me, what did your Chinese friend just say? Now I can explain it to this person in English, isn't it? Or I can explain it to the person in any other language that I'm familiar with. I can decode. Once I have gotten the semantic essence of it, I can now forward decode it into something else. Are we together, guys? Right? So machines which have this architecture, which have an encoder whose job is to listen and understand and get the semantic essence of the input, and hopefully as lossless as possible. The lossless is important, right? As losslessly as possible, like without losing facts and crucial details, right? If I can understand the essence of it, semantic essence, then you would agree that the decoding is a relatively easier task, isn't it? Right? I can decode it to something, but a crucial task is to be able to extract the semantic essence. So that is the encoder part of a language. And machines that can do this are called language models. When we think of large language models, large is a relative term. You don't usually find, many researchers don't use that term at all, actually, because what is large? Today's large is tomorrow's puny, right? So, but language model, this is the definition of a language model. A language model is a model that can take the semantic essence of the input, if it is language. Now, the language can be words. For example, the cow jumped over the moon. Or it could be a picture, the cow jumping over the moon, right? Or a girl holding a cat, whatever it is. So pictures are also, they are a visual language. It doesn't have to be a literate language, language as in words. It can be an image, it can be a video, it can be an audio file. Nevertheless, anything that can extract the semantic essence out of it and understand it in as lossless a way as possible is a language model. That is the goal of a language model. Because once you can do it, you can forward decode it to all sorts of tasks. So for example, the task could be converted to French. You could do that. You could do a sentiment analysis. Whatever the input was, is it a positive sentiment or a negative sentiment? And the decoder can say, oh, that's what it looks like, right? The question could be, for example, suppose you give two sentences. One, does the second sentence actually follow the first one, right? Or is it a non sequitur, right? Is it an answer to the first text, right? And so on and so forth. You could do a variety of tasks, or you could say, I've given you a rather long text. Why don't you summarize it? Or you could say, why don't you continue the story? I've given you the first line of the story. What happens to the cow after that, right? so on and so forth. All of those things are possible so long as you can extract the semantic essence of it, and then the decoder can forward do many tasks. Are we getting it, guys? So why is that relevant? People were trying to do it with something called recurrent neural networks, whose more industrial or robust implementations for things like LSTM. I won't go into the technicality of it. Just think of big brothers of recurrence and GRUs. And people also were working with text using convolutional neural nets. And what was happening is, if you remember, many years ago, the language understanding or the language as a language model, RNNs were not proving up to the task. They were the state of the art, but not proving up to the task. You could tell many a times if you had to just have a humorous moment, you could take text in your vernacular, feed it to Google, and ask it to translate to English, and something quite hilarious would come out. Anybody had fun with that long ago? Right? So, but today it doesn't happen. Today it's very good. And this is the watershed moment. In those days, it was with RNN. So Google had a project which they called the CargoNet. They said, okay, let's throw in everything. By the way, this story was narrated in one of the NVIDIA's annual events. They got the authors of Attention is All You Need onto the stage to recount how did they come up with this thing. And it starts with that. So they created a cargo. They started with CargoNet. C for CNN, those are convolutional neural nets. A for something called attention. And you learn about those technical things in this is for recurrence. Attention actually is the most intuitive and understandable. What is attention, guys? Today, at this moment, as we are talking, right? See, there are so many other things happening, right? There's some activity in the break room, the air conditioner is humming, and so on and so forth. Nevertheless, you're paying overwhelmingly more weightage like your focus is much more on me, right? So in other words, is the differential importance you give to the different pieces of the input. That is attention based on a certain context. The context is you're here to learn about drag. Right? So context defines attention. In my case, when I go hiking, context is very obvious. I go out hiking early in the morning. What's in my mind? Let's enjoy the sunrise, the beauty of the sunrise. Actually, by the time it's sunrise, it's already late. The first light in the sky, the first birds flying, and so forth. So I'm looking at the hills. All of a sudden, from the bushes, I hear a growl. What happens to my attention now? The sky has sunrise and sky and everything has disappeared, and I'm scanning the bushes for the coyote or the bobcat or something, isn't it? So that is attention. A context determines where you pay focus on. So there's a neural architecture for that. We'll come to that. So they were trying everything possible. And what Google was trying to create this architecture, what could Go stand for? Google. So CargoNet. Then what happened is when they did it, it did work, but then they did something called aberration studies. They wanted to know how much did CNN contribute, how much did attention contribute, how much did recurrent contribute. So a bit of history was that attention was a new kid on the block. People treated it as pixie dust. So if you made any neural architecture and you sprinkled a bit of pixie dust on it, attention on it, it just did better. That was the general feeling in those days. Right. And so obviously you have to bring in attention. They knew it does something useful. But when they started doing aberration studies, they threw away the CNN and they realized that the language model works just as well. Right? So they said, yeah, CNNs are more meant for vision tasks, computer vision images. Makes sense. Then the dogma was you cannot do language models without recurrence. That was the established dogma. So they said, okay, now we have attention and recurrence. Let's see what happens if we take away attention. So attention they took away. Let's say the performance goes down. Put it back. Then say, okay, let's take the recurrence out. And they took the recurrent out. And what they found, to their great surprise, is that when you take this and this out, it still does amazing, in fact, better. So when they noticed that, they brought more and more of the blocks, so-called attention heads, into the architecture. So if one is good, more is better. And they made a whole architecture out of nothing but this pixie dust, this attention heads. And therefore, and it was a transformative movement. The architecture they created is called the transformer. Right? They introduced the term the transformer, and now you know why the paper was called "Attention is all you need." Right? So when that happened, the big thing that happened is, and this is 2017, took a while for people to realize what happened. It had many other implications, like, for example, you could do parallelized processing and so forth. And of course, this architecture probably accounts for most of the trillions that NVIDIA is worth, right? Because it has a massive computational need. Right? So when transformers came about, you had a really powerful language model. And people began to ask this question that what does it mean for the search? Right? What does it really mean for search? Because we are producing, the encoder is producing some latent representation. Actually, much more technically, language model is not the whole architecture. It is, but it is also peculiarly the name given to this inner, that, you know, the private diary of the machine, what you wrote in your native tongue. So let me just call it machinese. So imagine that you heard Chinese. If I were to hear Chinese, my first instinct would be to write it in English or my native tongue. So in the same way, the transformer has its own language, let's call it. And that language, this private language of transformer that it writes it in, just for the sake of argument or clarity, we'll call it machinese. Right? So it writes it in machinese, and then you can forward generate it to whatever task, decode it to whatever that you want it to decode it to. Does that make sense, guys? So it's a private language. So actually, strictly speaking, language model is input getting modeled into, written into machines. So some people also call the latent, this is the, people also use the word latent representation. That is the language model sometimes, right, in literature. But anyway, what is the implication of that to RAG? How do we connect the dots? It's quite interesting, actually. People knew there's a you can make the ranking, page rank, this, that, BM25, etc., as good as you want. But there's a fundamental limitation with keyword search. The problem with keyword search is English language is infested with ambiguity and a lot of flexibility and variety. So in particular, there are homonyms, there's polysemy. When I use the word, one almost oft-quoted example in our field is, if you use the word bank, what does it mean? Right? You may deposit your money in the bank. You may be sitting next to a river bank, right? Or you may have swam across the river to the other bank, right? Your airplane may be banking left to align with the runway, right? Or your friend may be banking on you to bring the pizza. You see, the word bank admits many, many meanings. Therefore, if you put it in a very simplified way, if you put it in an index like this, you see that now you have a problem. You will get documents that deal with all sorts of meanings of bank, isn't it? And you will do relevance ranking. So you can ameliorate the situation. You can sort of mitigate the problem through all sorts of clever techniques afterwards in relevance ranking. But the problem doesn't go away, because at the heart of the problem is this fact that the meaning of a word is often in the context, the words around it, right? In the sentence around it. So when you say, nah, which is the nearest bank I can go to deposit cash? The word bank, its meaning gets completely disambiguated. Would you agree with that? Isn't it? So the context, actually, the contextualized meaning, there's a contextualization to a word that imbues it with its full meaning. Sometimes the meaning is not there fully in the word. Sometimes you don't even have to give the word. Suppose I replace the word, where do I go to, which is the nearest X where I can deposit my cash. Everybody can infer that you're probably talking about a bank, isn't it? So the meaning is often partly outside and almost sometimes completely outside the word itself. That harks back to attention, actually. So what does the word need to do? It needs to pay attention to other words, right? To figure out, bank, who am I? What do I mean? And that was the attention mechanism. And so what it opened the world to is this concept, and I'll just rush through this now a little bit, is that if you let the user ask a question, let's say, what do happy cows do? Right? And if this goes in to the encoder, and what you get is a latent representation, right? These days, we call this embedding vectors, right? So let me just call it X as a text, embedding vector associated with the text. So the amazing thing is that these vectors, isn't it amazing that in a vector, multidimensional vector, you can capture somehow the full meaning of the text. A machine can do that, right? Or almost the full meaning. There's something is almost the full meaning of the text. How is that possible? Right? Let's talk about, and I'll give you a basic intuition of how this works. Let's think of animals. Let's talk about only your pets, right? So suppose you have pets, right? What are the pets that we typically have? Dog, cat, parrot, um, what else? Goat, rabbit. Okay, let's go with these five. So what do you do? Let's try and see, can we make it into words? What we can do is we can make a table of features. A dog has how many legs it has, right? Four, four, two, four, four. Let's take an example, right? Weight, dog would be relatively heavier, right? My dog used to be, let's say, on the slightly heavier side, 90 pounds, right? The cat wouldn't be 90 pounds. What's it, 20 pounds? Fair enough, right? A parrot would be what, 5 pounds? Well, that would be a heavy parrot, 3 pounds, right? A goat would be more like 50 pounds. A rabbit would be, let's say, 10 pounds. Does that look reasonable? Right? And now let's think of weight and color or color, and you can go on with attributes. Do you realize that the more attributes you attach, the more uniquely you can specify which animal it is, isn't it? So imagine that you tell a machine, I'll give you an animal, but you must store it as a vector. What will it do? Sooner or later, given lots and lots of different cats and dogs and so forth, it will start putting it into a vector space. So all the dogs will start landing together, all the cats will start landing together, all the parrots will start landing together. You get the basic idea, isn't it? They will get separated out as vectors. But interestingly, now let's try to relate it to the word embedding, embedding as a vector, because this is crucial. How many of you have heard the word vector databases? All of us, right? What do vector databases contain? This vector. This is all they contain, right? So this vector, it has taken on a lot of importance these days. So now let's try to relate to it. See, when we use any word like a dog, and imagine that I ask you to completely understand that word. Now you start, if you were to decompose it into all its constituent implications, you would need many axes, many so-called columns, or what mathematicians would say, many dimensions, isn't it? And so it turns out that human language is so rich and complex that to actually capture it, typically you create vectors. The typical embedding vectors that you create for text, for any given text, belongs to a d-dimensional space, which these days are from 1000 to 4000. 1 to 4,000 dimensions. It just speaks to the richness of the human language, that any piece of text, we talked about word, but now talk of the whole text. The text takes some meaning. So there is an embedding space, a world. So imagine an abstract world of just meanings, right? So if two dots are close to each other in that abstract space, they represent somebody's thought, somebody's text that have very similar meaning, semantic content, isn't it? But they need not be just words. They can be images. I can show you a picture of a cow jumping over the moon. And that, the semantic content of that is the same as the textual description. The cow jumped over the moon, isn't it? And therefore, it should also end up in the embedding space very, very close to that. So the first big insight is, let us convert text into embedding vectors. That insight leads to profound consequences. The consequences it leads to is this. Suppose all the documents we had, let's go back to our documents. The cow jumped over the moon, the Apollo landed on the moon, the cow was in the meadow, right? You realize that these are semantically vastly different statements, even though they have, for example, D1 and D2. The cow jumped over the moon is probably there from a nursery rhyme. I think it's Diddle Diddy or something, right? Kids nursery. Actually, by the way, when people say enjoy, I'm over the moon, it actually happens to come from that nursery rhyme, right? So the cow jumped over the moon is a kindergarten thing, expression of joy. On the other hand, Apollo landed on the moon seems like a factual historic thing, isn't it? Inspires joy of a different kind, perhaps. The cow was in the meadow. Where else would you expect it to be? That kind of thing. So familiar environment you expect it to be, other than the barn. So now what you do is you take all your documents, DI. For now, I will, so when I say the word document, just for simplicity, document is the same as a sentence, is the same as a paragraph, so forth, right? So people in our field, they tend to use these words synonymously. So when they say the word document, they might just be meaning a sentence, right? And they often mean chunks. So there are little nuances. There are nuances. You break up a document into smaller chunks, and you may want to. The unit that you convert into a vector is a basic unit. But to be just sloppy and get the ideas across, we'll just use the word document. Is that okay, guys? I don't want to bring in the nuances at this moment. So document D1, D2, D3, all of these. So let's just say DI, it becomes a vector embedding, right? So now here comes the crucial insight. If you just remember document I and its embedding vector, document I and its embedding vector, you happen to have a private notebook, you note it down, right? Then what you do is, let's say here are documents, there are documents, and let me just take it this way. Here are documents all over the place. So each of these dots are, what are they? They are the vector representations of the documents, isn't it? The encoders, machines of that document, isn't it? Because we write in English, let's say, but transformers write in vectors. And so whatever you said, it says, oh, this vector. And so it wrote in its machines and it became a dot somewhere. Now, suppose a user comes and asks a question. Let's say that you have a question now, which is some question. What did the happy cow do? Can you guess when the machine converts it into machinese, would it be reasonable to say that it will land very close to the text that says the cow jumped over the moon? Does that make sense, guys? Doesn't it make sense? It's unlikely to land next to Apollo, isn't it? Maybe the next close statement would be the cow was in the meadow or something, was grazing in the meadow. Right? So by doing this thing, you literally can say, I use this descriptive phrase, that the embedding sounds so abstract, embedding space, right? I call it the metropolis of meanings. So imagine a city which is not populated by buildings and by people, but actually the meanings of things, meanings of text, meanings of thoughts, and each little person represents in that metropolis the meaning of some text. That's literally your embedding space. Right? So you would agree that if you just pick the nearest neighbors in the embedding space and ask which documents do they correspond to, they would form perfect search results. Guys, does that make sense, guys? Are we following the argument? Right? It is obvious because it's unlikely to land adjacent to the statement that says that you need like an induction motor to repair this fan. That statement is not going to land proximal to that thing. The meanings are entirely different. And thus is born what you just learned, picking up the, so what is the last leg of the puzzle? Just pick the k nearest neighbor, KNN search in embedding space. Are we together, guys? In the embedding vector space, find the k nearest neighbor and do a reverse lookup which documents were there. And they are your search results. Are we together? This represented a watershed moment in the search industry. This was the birth of AI search. Today, more or less, the proper birth of AI search. And it also opened up the possibility of multimodal search in a genuine way. Because nowhere did we say that what goes into the encoder necessarily should be text. It could be image. Right? And you need a different kind of encoder. And in fact, the work that brought it about was another landmark research paper called CLIP, etc. We'll get to that. But and I'm skipping through a lot of very important work that was done in the field, but that's for a separate course. But this is the gist of AI search. But so now what do we have? We have a much smarter search, isn't it? In the very least, guys, even if you don't do RAG, doesn't it make common sense that in the organization, wherever you're using the traditional search, you should augment it with AI search? Isn't it? And that is it in the enterprise. Highly useful. That's why I said it is very, very hard to argue against RAG and AI search. So this is AI search. Now comes the second part of it. See, the search industry, the formal name that people give to search has been retrieval. This is often called the retriever systems. Retriever system. Big mouthful. What does it mean? It reminds me of my golden retriever. I would throw something, hide something, and she would go find it wherever I hid, and she would drag it out and proudly bring to me. She would search. Right? Retriever systems are just fancy words for search engines. Search systems, searching. Are we together? So there's a whole field called information retrieval, which is all about search. So you give it an input, a query. What will it produce? It will produce top K documents. Top K candidates, isn't it? Documents, texts. Text is better because when you think of document, you think of massive PDFs. Actually, it returns little chunks, little pieces of text. Let me just say, would it be better if I use the word text? It's more intuitive, isn't it? Top K relevant text. And I'll sneak in the word relevant because I hope K nearest neighbor implies relevance, isn't it? It's a redefinition of relevance. Now, to complete the picture, and I'll complete the picture for the break, here's the thing. Search has been around. We have been Googling. But when you Google, it is sort of, ordering a bicycle, and the bicycle comes, and you anticipate. You're just sitting there. Imagine that you're a young kid and you just ordered a bicycle. And the bicycle is supposed to come, and the moment you are there, you tell your friends, I'm going to ride over to your house. But what comes is a box of parts. The bicycle did come, You have to sit and assemble it, right? So what happens when you search for something? Used to a few years ago, when you would search for something, even in powerful search engines like Bing and Google or Elasticsearch in your enterprise, you would get a list of search results. Did it answer your question? No. What do you have to do? You have to sit and build a bicycle. You have to read those documents and find the answer to that question. Right? So that task was yours, isn't it? And therein comes the second part of the puzzle. Now you can say, now wait a minute. Didn't we just create a very powerful language model whose job is to understand language? So why can't we do this? Let us feed these search results into the language model. So what will it do? It will convert it into machinese, right? And then we will give it the user query, which also it will convert to machines or whatever it wants to do. But we don't care. And we will say, now that you have understood all of this, because that's what you do, you're a language model. You understand the semantic essence of the question in the documents, the top case search results, isn't it? Therefore, you're capable, the decoder part of it, you're capable of producing an answer. Am I making sense, guys? Yeah. And therefore, those things, of course, are popularly called a LLM. So you have a generator part, isn't it? And typical generator these days are what we popularly call large language models. Notice the word large language model. Now you know what the purpose of the language model is there in all of this. Because you're literally saying, here is it, and by the way, here is my query also. Use this results to answer my question. Right? And then you don't have to read the docs. It has done that. It has understood and it answers the question. That value itself is inarguable, isn't it? Why would you just sit and look at search results, right? And how many of you, by the way, have gone to page 2 of any search results, right? There is a joke going around that NSA hides its secrets on page 2 of the Google search results, right? No, nobody ever visits that, right? So you just give it to a machine. It will understand and it will answer your question. So retriever and generator. Can you guess what this architecture is called? Anyone? RAG. Literally, this is RAG. Every time I think of RAG, I think of tone shirt. So I made it a point to have a shirt today where the pocket is torn. Right? So it's RAG. We have RAG. It stands for, it's a very technical term, retrieval, augmented, generator. So this needs a little bit of an elaboration, and I'll give that, and then we'll take a break. We are almost done. So that's the birth of RAG as an architecture. It has two core components. In the minimum form, guys, we are the kernel of the idea. Now, let me again emphasize, if this is all you do in your RAG, I guarantee you'll create a mediocre RAG. But nevertheless, way back in the mess of prehistoric time, as in way back in, let's say, first quarter of 2023, right? This is how people used to build, or we all used to build RAG systems. Are we together? But much water has flown down the river, and now we don't do it like this. We do this. This is the core still, but we have to bring in a lot more. Right? And what that lot more is, it takes a long time to learn from experience, of course, and so on and so forth. But this is RAG. Why is it called Retrieval Augmented Generator? See, I will not look at it this way. I'll look at it the first way, from a retrieval system perspective. If you take a retrieval is just a fancy word for search engine, isn't it? So you could look at it from a search industry perspective, and you're saying language augmented search, isn't it? Language model augmented search. Right? Because all you have done is search results, you have added an extra functionality at the tail end to produce an answer. But actually, you can look at it backwards, and the first papers looked at it backwards for a reason. What used to happen is, and the problem still persists, though to a lesser extent, LLMs, these large language models, they have learned from a whole mountain of data. Everything that's in the public domain, they have studied. So one easy way to think about them is, there are 1,000 PhDs in like in 1,000 fields, right? So imagine if you remember the story of the Wizard of Oz, right? You talk to the wizard behind the curtain. You ask a question in the wizard. I don't know. Are you familiar with the Wizard of Oz story? Right? So the wizard answers from behind the curtain. Well, in that case, the wizard turns out to be fake, but imagine a real wizard, right? So it's like 1,000 PhDs behind the curtain. And when you ask a question to an LLM, wow, GPT-5 or Anthropic or Cloud or Gemini or DeepSeek will come out with a lovely answer, right? And you thought, what is it that it doesn't know? It seems to know everything. It does know everything in the public domain, right? Because it has studied everything, right? And for months and months, with this big brain, it has been studying everything that humanity has produced. So there, but it leads to a problem, actually a problem for this kind of architecture. See, you want to use the large language model for its language model ability to understand the semantics of, for example, the top case search results and the semantics of the query and use the results to answer the question, isn't it? You want the language model capability, language understanding capability. So let me park that word, language understanding capability of the language model. That's what you want. But there is another thing that it's very good at. Remember, it's also 1,000 PhDs. So it can be a bit of a nuisance. Why? You ask it a question, the answer is not there in your search results, but it knows the answer, right? So it will answer it anyway. Do you see that? Right? It will just answer it. And what gets worse is sometimes it is over eager to please, it's over eager to answer. So even when it doesn't know the answer, it will make one up. Right? So actually, that reminds me of a kid's joke. Can I say that? It's a silly joke. Why do scientists not trust the atoms? And the answer is because they make everything up. So that's true of the LLMs. If they don't know the answer, the fear is they can make it up. And that phenomenon in which they just make up an answer is called hallucination. So hallucination represents one pathology, answering something which is not there in your search results, but you know the word that you use is parametric memory. Right? Parametric memory. That's a technical term. Why this fancy term? See, the LLM, it is made up of knobs. Right? Imagine that's a very complex piece of machinery with lots of knobs and neurons, and there are lots of knobs in there. Those knobs are called parameters, theta, weights and biases. One of the remarkable things is, even though they're just numbers, there is no database baked in there. And for reasons that we don't quite understand, we actually don't fully understand. We have some sense mathematically of why it happens. But this machine, which is stateless, remembers things. It remembers all that it studied. Now, where did it squirrel away all that information? How is it that it's remembering? Because we didn't give it any space to remember facts, remember things. That is a bit of a deeper technical topic. I don't think anybody has a full understanding, but to the partial understanding that we have is very fascinating, very mathematical. And if you engage with me, we can go on a little rabbit hole down that journey. But it does happen. It remembers. That memory is called the parametric memory. Now, one way to look at it is LLMs used to hallucinate. Here's a classic case where they will hallucinate. You trained a model today, right? Today is August, some date in August 2025. Your future version in December 2025, you use the model and you ask it a question. So here's the thing. Let's look at the last presidential election. The Democrats changed their candidate half midway, isn't it? It went from Biden to Harris. It's Kamala Harris. Yeah. So Then what happened is, if a model was trained before the transition and you asked who are the leading presidential candidates, it would happily say it's Donald Trump and it is Biden, isn't it? But that would be factually wrong, right? The other thing is, that is one problem, datedness. Let's park that, and we are almost done. Datedness is a problem, right? Let's say pathology, datedness, hallucination is possible. The other problem that you have is the fact that the people are asking this question. Look, we all love ChatGPT, but all it knows is public knowledge. But our enterprise, which is so great, right? I'm sure all of you think that your enterprise is so great, it should have been much bigger, right? So that enterprise has a vast amount of data, facts, knowledge, and you're using traditional search engine on top of it and having to read the answers. So if you ask ChatGPT, it is not able to answer specifically questions about the circuit design of your silicon, your particular product circuit design, isn't it? So why don't we? So how do we solve that problem? And the answer to that is exactly this. So what you do is you take your proprietary knowledge, you put it into the retriever system, search. People trust search systems, retriever systems. Right? Every organization has a retrieval system in-house. Elasticsearch, this, that, right? They have it. People have known how to do security over it, role-based access control and all of that. They baked it. So what they can do, given a query, they can just look into search results that this user has access to, produce the results, then give it to the LLM and say, you don't know this implicitly, but here are the facts. Now, you knowing these facts, can you answer this question? What will it do? It will mitigate the hallucination, isn't it? And more importantly, it will overcome proprietary. I'll just. So you're on the fly teaching it, and then it will solve the datedness problem, right? If it has access to the latest news. And so what people looked at it, and that's where the word traditionally came. The generator was the LLM. And to make the generator better, what people said, or make it, for example, useful for enterprises or many such contexts, why don't we back it up with a retrieval system? We'll give it more knowledge on the fly in the prompt to use to produce the answer, and you'll get better answer. So guys, do you see that you can look at the same system backward and forward as two different value propositions, right? And that is the value of RAG. So what I would like to do is, with this sort of overview knowledge, I would like to now show it to you in action and then show it to you in code today. But today you won't code. I will show you code. I'll show it to you in action. But Wednesday when we meet, again, as I said, please do bring your laptop. You don't need much. You just need to know two things. GitHub. There's such a thing called GitHub, where people put their projects. You have to be able to pull it. And the second thing is you need some familiarity with Python and a tool called UV. So, guys, I'll take you through a small journey through the code to see how all of these ideas that we talked about, actually, they're closer to reality than you might have thought possible. So I'll go into the notebooks and examples. What I'll do is show you everything that we talked about. We'll bring it to code. We'll show it to you in action. And then you can tell me whether what you think of this whole big thing called AI search. So first we'll do AI search, and then we'll go into RAG. Is that okay, guys? We'll do it in a two-step process. Just a little bit of a background. By the way, all of this code, where is it? Those of you who are familiar with what GitHub is, if you go to the support vectors GitHub, you'll find that it is a project called RAG to Riches. Literally the name of this little event. Do you see RAG to Riches? You can pull all this. Huh? It is all there, just for you to know. And next, I'll walk through all of this today. If you already are very comfortable with coding, go ahead and smarten up on it over the next day, and we'll meet on Wednesday. So, semantic search. As we said, traditional search, one would search a corpus using a keyword-based search engine. We understand the limitations of those, right? We talked about it in the morning. How would you really like it to be? The way you would like it to be is you would like it to be like this. The user doesn't give keywords. So just to caricature this a bit, imagine. So I tend to lose my keys every day and my wallet every day. Right? If I don't lose my keys, I've lost my wallet. If I haven't lost my wallet, I've lost my cell phone. Right? So people have to help me, my family, piece the things together. Right? But when let's say that one morning I'm there at home, and if I just keep uttering the word keys, 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 it takes people time to understand what do I mean by keys. Wouldn't it be better if I said, I have lost my keys. Have you seen it anywhere? Isn't it? Unfortunately, we communicate in natural language, but most of us before the 5 years ago, how were we communicating? Using keywords. Even now in your enterprise search, what do you enter? Keywords, isn't it? And that's the problem of it. Humans don't communicate well with keywords. And keywords are anyway deficient of semantic content, right? Full semantic content. So it becomes a hit and miss. Right? It would be much better if we express what we are looking for as natural language so that the machine understands the semantics of it, went and found what it wanted. So somewhere in between, magic happens, and then you get a result that's relevant. Please go ahead.
So I think slightly differently. The way that it happens is that the more expert you get, the more you eliminate context, and so and you go deeper. Like early in my days when I used to go into auctions, in the auction they would only say 32, 33, 35, and that is where they would completely take away like if it was 10,032, they would not say 10,032, 10,033. They would say only 32, 33. So the context has to be taken away because you're so much into that context.
Because you bring the context.
Yes.
Yes. So that is the main point. Actually, you touched upon an important point in RAG. See, what happens is, and with human beings, right, there's always something called, and you alluded to something that's related to a concept in psychology called the theory of the mind. What happens is, when you and I talk, I have a pretty good understanding of how you are thinking. So communication is efficient because there is an implicit context between us, right? Less words are needed. But when you go to a search engine, there is no implicit context. And one of the purposes of RAG, right, a good RAG system, is to contextualize human queries. So one way to illustrate it, an analogy is, imagine that you are a busy computer repair shop, right, or electronics repair shop, and customers are streaming in and out, some bringing the broken defective equipment, some picking up repaired equipment, and one customer walks in and says, 3 days have gone by, what's up with you guys? The customer service representative at that moment is completely, what is missing here? Context, isn't it? So what will a good customer service representative there say? I'm really sorry, but let me help you. What's your name? What did you leave here? And you dig up the person's context. You add that, and then you come to know into the record system that, oh, this fellow left the iPad which had a battery that's dead or something like that. You're seeing that, right? So contextualization is actually one of the crowning features that RAG brings to the table, right? Because it removes the deficiency that human beings, when they engage with traditional search systems, they were not in the habit of doing that. They wouldn't bring the context, and they would forget that a search system that's catering statelessly to 100,000 employees or to a billion users inherently doesn't know who you are, right? Or what your context is. So RAG systems actually bring that contextualization. So anyway, continuing forward, What we want is magic should happen and only the relevant search results should come by, right? This actually is the main purpose of RAG, not just meaningful results, but the right answer should come by. And good RAG systems go over and over. They don't do just take top case searches, give it to LLM. They look at the answer, they say, have we answered this question fully or not? Then they go back and do a few more rounds. So have you noticed that sometimes when you engage with these powerful RAG systems like ChatGPT, agentic RAG systems, or Perplexity or Anthropic Cloud, Gemini, it takes a long time before it produces an answer, isn't it? What is it doing? It's not just doing one pass through the whole thing. It's really mulling over the whole thing, searching, saying, okay, do I have enough to answer the user's question? If not, what do I need to search? And there's a concept in search industry called exploratory search. What happens is you start searching, you get some facts, you learn from the facts, and then you say, oh, now I can better answer the user's question. Maybe this is what I should do, right? Are we together?
Yeah.
So you go step by step. So that's it. Anyway, so we'll go through. Now, how does it happen? We talked about it. A document becomes a vector in a high dimension space. By the way, when I said high dimension space, I gave you the intuitive idea that weight and dog of a cow, etc., attributes. In reality, those dimensions are abstract. Right? We don't know what they are. That was just to convince you that you do need a fairly rich dimensional space. There's another reason for it, by the way. When I said that and I gave you the intuition, if there's any mathematician around you, say, wait a minute, you've missed the main reason. Actually, the main reason is that in very high dimensional space, the chances of getting a false positive or a wrong answer gets mitigated significantly. Because in high dimension, one of the weird things about high dimensions is there's just way too much space there. So everything that is unrelated moves far away from each other. So if two things are nearby, then they are genuinely related, right? So if a query lands next to a document, you can trust that this document is somehow related to this query, right? So you use, that's a mathematical reason. But anyway, we'll leave that aside. What happens is that you end up with this. Now, this MKDocs has mangled it up a little bit. I'll take you through the code here. So what happens is that you have a document, becomes a vector. So you get pairs of documents and vectors. By the way, by documents, I mean paragraphs, sentences, text, whatever. Remember, D is text. Don't think of it as anything else. So you have a text and vector pair, guys. Okay. What do you do now? If a query lands somewhere, you just find the relevant documents around it. It's a review of what we talked. How do we find similarity? It turns out that Euclidean similarity doesn't quite work, right? Because in high dimensional space, everything is far away from everything else, right? So I often give this example that in the Bay Area, if you want to meet your neighbor, you just open your window and knock at the guy's window, right? The houses are so close, squished together. Whereas in Wyoming, if you want to meet your neighbor, you get into your vehicle and drive half an hour, right? So that is how high dimensional spaces are. Everything is too far away from everything else. So the concept of Euclidean distance doesn't quite work. You can't start driving to the other. But there is one concept of distance that does still survive in high dimensional spaces. It is the distance of angular distance between 2 points. See, when you lie down at night and you look up at a summer sky, right? These days it's quite pleasant. What do you notice? You see that star, Orion's belt, and near there, if you go turn left there, you'll get near Sirius. Actually, Sirius and Orion are way, way far apart. But to you, it appears close because angular-wise, it looks near, isn't it? Or the three stars that form the belt of Orion are. Do you guys know what I'm talking about? Orion. The belt of Orion, they're close, but they're actually not close. They just look close, angular-wise. So the angular distance, which is measured by your humble cosine theta, remember, angular similarity survives in high dimensional space. It still does very well, and dot product survives. So you use that distance. We won't go into that. let's take some sentences. So what I did is, for the sake of this example, I took just, so imagine that you have a company with gazillions of documents, but we will miniaturize gazillions to some 15, 16 documents. But I've hand created a variety of documents, right? One of them is, uh, anybody likes this one? It was Brilling in the Slithy Toes. Okay, it's Lewis Carroll. People with a mechanical bent of mind, they are big fans of Lewis Carroll, Alice in Wonderland, and so forth. Right. So this is a sentence. I love it because not a sentence makes sense, but if you read it aloud, it seems to make sense. Right? It was brilliant in the slitty toes, the gyre and gimble in the wave. Sounds so dramatic, but not a word makes sense. Right? So anyway, the other one is just for variety. I took some of my favorite passages. The Tale of Two Cities, the famous quote by Dickens. It was the best of times, it was the worst of times, and so forth. Another one, and another one. This is another one from Tale of Two Cities. And then Mark Twain. Um, the dog is a gentleman. I hope to go to his heaven, not man's. Right? So Einstein's quote: if a man aspires towards a righteous life, his first act of abstinence is from injury to animals. And Tweedledee and Tweedledum again, Lewis Carroll. Alice. Then a few quotes on golden retrievers, dogs. Keats, a thing of beauty is a joy forever. Attention is all you need. That famous paper that I talked about. This is the abstract. Back propagation, a very technical topic in neural networks. This is it. Lucy's famous poem. It's a poem I like very much. Of Wordsworth and Davis and so forth. So as you notice that I've created a corpus with reasonable variety, technical documents, gibberish, and so forth. We create a search engine over it. So what do we do? First, what do we need to do? We need to convert every document into a corresponding vector. Right? So suppose I have 16 documents, I'll get 16 vectors. Does that make sense? Isn't it? Let's do that. So to do that, you need an encoder. Remember, something that understands the semantic essence of the text. So that encoder is a model, and we usually call them embedders because they produce vector embeddings, isn't it? And we won't use a vector database, at least in the first example. Our vector database will be literally a list in memory because we'll do nearest neighbor search right there in memory. Just to keep it simple, just to get the ideas. So we have an embedder. When we give it all the sentences, what do we expect? We expect all of them to become vectors. How many vectors will we get? 16 documents going, 16 vectors will come out, right? So there'll be 16 rows. But each of the vector is 768 dimensional, right? So I wrote this code because when you run it on your laptop, I wanted to make sure that it runs on your laptop, right? And so I took a tiny little embedder. Distill, whenever you see the word distill, it means shrunk, right? A bigger model has been shrunk down, its knowledge has been distilled down to a smaller model, right? So distill. So I took a small model, it produced an embedding of 768 dimension, which looks big, except that actually you go to production typically with embeddings that's 1, 2, 3, 4,000 dimensions these days. So this is it. So here's one of the great paradoxes of the world of AI. So here's this poem. It is brilling in the slithy toes, etc. When the machine converts it to machinese, interesting thing is machine understands English. But the reverse question, do humans understand machinese? I leave you to read this and tell me whether you can look at these numbers and say, aha, it is brillig in the slithy toes. How many of you can do that? So this is the paradoxical asymmetry of the AI world. AI understands us. We don't understand its language at all. Right? We don't understand machines at all. Something worth remembering, actually, reflecting upon. Now, let's go search for something. I search for a friendship with animals. a text, right? And let's see what search results come out. I asked for top 3 search results. I want you to reflect upon the word. Think of it from a keyword search perspective. A friendship with animals. What are the keywords that you can pick in that? Friendship and animals. So a traditional search engine would populate the search results with text that have either word friendship or animals, or hopefully both. Yeah. Isn't it? That's how a traditional search engine would work. Now let's see, how did an AI search fare in this context? It said something quite interesting. By the way, a disclaimer, I love dogs, right? And I used to have a golden retriever, and this is my other dog. I think my daughter took it away. There's a lab now. So it says a friendship with animals, and it says golden retrievers are not bred to be guard dogs. Actually, pay attention to the context. Are not bred to be guard dogs, and considering the size of their hearts and their irrepressible joy and life, they are. If you go through, okay, I wish I can go through. Okay, I'll go to the this thing itself and see where the text is. Yeah, here also. Yeah, are not bred to be guard dogs, and considering the size of their heart and their irrepressible joy and life, they are less likely to bite than to bark, less likely to bark than to lick a hand in greeting. In spite of their size, they think they are lap dogs. And in spite of being dogs, they think they are also human. And nearly every human they meet is just to have the potential to be a boon companion who might at any moment cry, "Let's go," and lead them on a great adventure. Long text. Did you find the word friendship or any animal anywhere in the text? Nowhere, right? Think about, just ponder over it. Think what kind of a person would write that sentence? What is the emotion reflected in that sentence, in this text? Surely a person who has a deep feeling for animals, a deep friendship for animals, isn't it? And now reflect upon the fact the AI search latched onto that this is the best text to reflect friendship with animals, isn't it? And now think back at what I just did. I deliberately gave it a hard query. I asked it not to search for a Coca-Cola, but I asked it to search for an emotion and text that reflected that emotion. Realize that is only possible if a machine can understand the semantic essence of text. And that is the revolution. Do you get that, guys? That is, you see what a watershed moment it is when you can create a machine that can produce this as your first search result. That is the power of AI search.
One question for the experiment. Did you only use the encoder and the decoder and no
just the encoder?
Model?
Just the encoder part. See, the word large language model has become sort of overloaded.
Sure.
And encoder is a language model too. It's part of the transformer because it's understanding the language. And I could have used a decoder. So we just use the word embedder, produced an embedding. Today, embeddings are done either with the encoder or with the decoder. If you go to the leaderboard, the state-of-the-art embedders these days are actually decoder models. They are encoder-decoder models too. And they are encoder-only models too. But the main thing is a language model's job is to create machines from text and then do a task.
But the interpretation part, using the whale language models, structure a sentence, stuff like that.
Yeah,
that part was not used.
Not used at all. This is pure retrieval. Yeah.
Right.
So the generator is silent. There is no generator here.
Yeah.
This is just the search. Remember, just the retrieval.
Got it.
And we'll go to the RAG. And by the time it's midnight, you'll feel happy. So hang on.
And the encoder that you use there is a standard function.
It's just a model. It's an AI model. It's a language model. Right? It is actually called the encoder language model, transformer, encoder part of the transformer. There are many, there's a bit of.
Can you go to the code where you were creating those vectors? The function.
See, here's the thing. Let's go over it.
Yeah.
At this item number 2, I take a model. I instantiate the model, right? So the model, embedder is the model. What is the job of the embedder? Embedder, this entire model, this language model, it text in, vector out, right? So in other words, English in, machine is out.
Yeah.
Right? Semantic understanding out. That's it. Let's do that. Where do I do that? Oh, look at this. Embedder.encode, and I give it the list of sentences. So for every sentence, every text, it will produce a vector. That is it. As simple as that. You see that, right? And after that, I just do a similarity, KNN similarity search and so forth. The rest of it is straightforward. I look at semantic search into the embeddings. Given the query, convert it also into an embedding, and then tell me what are the nearest documents. Those embeddings are there, nearest search, right? So guys, look at the second search result. Does that contain the word animal or friendship? That too does not contain it, isn't it? If you're lucky, a golden retriever will come into your life, steal your heart, and change everything. I can vouch for that. Right? But that text also reflects an abiding love of animals, isn't it? A friendship with animals. Look at the third search result now. If a man aspire towards a righteous life, his first act of abstinence is from injury to animals. This is Einstein quote. Here the word animal is there. Finally, you got a search result which would look like coming from a keyword engine. Do you see that? But it is number 3. How many of you feel this is really insightful to see AI produce search like that? See, guys, what happens is we as engineers we get so lost in implementing things. Sometimes we don't get time to step back, reflect upon what exactly happened, right? What are these machines capable of? This is what you're seeing. But we can go further. In a keyword search, you can only give text. But language, the fundamental definition of language is a vehicle of communication, isn't it? Like the old saying goes, a picture is worth 1,000 words. Picture conveys as much as words can convey, descriptive words can convey, isn't it? Videos convey. There are silent movies that do a perfectly good job, right? And so forth. The videos are there. And of course, audio files are literally words. What if I gave the search engine an image? Now, what is an image to a machine? Pixels are just floating point numbers, right? 3 channels, red, blue, green channel. Each channel contains a matrix of numbers. We see a dog. Does the machine see a dog? Normally, no, isn't it? But if you give it to a language model, what will the language model do? It will say, vision is a language. Image is a language too. I can understand it and come up with a semantic essence. And the semantic essence, why should it be any different from if you had described it in words? The particular breakthrough that made it possible was a research paper clip. Now it's old history, but so there you see in the code, the clip model being used. It's a vision transformer model. It does exactly that, and then you can search into text. And when you do that, let's look at it. We'll embed this image into the vector space, right? And then we'll search for something. We again search for the query. What is the query now? Query is the image, right? Something we can never do with keyword. So this is multimodal search coming into existence. And what does it do? Look at this. From the search results comes out the text saying golden retrievers are little children. For the love of this furry dogs, a smiling dog. Right? Do you think the machine has understood what it's looking at? Isn't that magic that it can do that? That's the beauty. We formally call it multimodal search. Today, we sort of, oh yeah, machines can do that. But isn't it fun that it can do that? That's the power of a language model. So remember, language model means understanding some language form, understanding the semantic essence of that. Right? text, image, whatever. That is what the word language model in LLM really means. Now, you could do the other way around. You could give text as query and say, can I search images? I can take all my family pictures. By the way, one of the projects that people do in our boot camp is everybody has a huge set of pictures, right? And then they have gone on vacations and so forth. The beautiful thing is you can create a cross search between all your pictures and all your narratives, right? Yes, go ahead.
Sarcasm.
Sarcasm. Machines used to not understand that, but they're getting pretty good at it. So much, as I said, progress is very rapid. So now what I'll do is we'll take image. By the way, this is open source image, Unsplash. Unsplash has donated 25,000 images into the for people to use for research and so forth. So you guys can all download it. I just took 25,000 photos of everything: house, boat, hills, road, right? Whatever it is. Now what we will do is we'll create, you convert them into the vector space embedding, right? You do semantic embedding of the image. Once you have done that, let's search for it. And here is the fun part. I will give it a deliberately. Do you see this query, guys? Maybe I'll increase the font size. To love a dog, right? Maybe I should do it through, maybe this looks clearer, is it? I don't know. Let me see if MK Docs makes it look clearer. Yeah. Query. Oh, no, it doesn't do that. MK Docs handles stuff. So we'll have to look at it through the Jupyter Notebook itself. There's something called Jupyter Notebook that is very popular amongst our community. So to love a dog. Do you realize that I didn't say dog? That's too easy, isn't it? I deliberately gave it an emotion, an active emotion. Not only that, an emotion in action, right? And see what happens. How many of you would say that this is like absolutely on the dot, right?
So
Okay.
all this was possible because you kind of vectorized these images.
Yes. Put them in the embedding space and the query also in the embedding and pick up the k nearest neighbors. That's all it is. That's the power of mathematics, you can say, and the power of language models. Isn't that amazing? Right? So guys, you get the feeling for this. See, look at the first picture. It is not just a dog, but would you agree that this picture embodies to love a dog? Embodies, not embodies to love a dog. What about this? Guys, can you please get out of Zoom if you are on Zoom? Audio part of it. Yeah, look at this. Any one of these guys. How many of you, by the way, are dog owners or cat owners? Okay, so so now suppose you say house near a lake. House near a lake is what? See, there's something interesting about a thing. House near a lake can be taken factually, but the phrase house near a lake has an emotive response, a cultural response. In this hectic life that we live, half of you dream of having a house next to Lake Tahoe quietly and retreating to it, isn't it? Maybe some of you have that. It evokes a sense of serenity, peace, isn't it? So the beautiful thing with AI search is it is not factual. It sort of captures that. And see, would you agree that these are not pictures of ugly houses or industrial houses next to, right, a lake or something, but they also capture the emotive aspect of it, right? So this is the beauty of, guys, this is the beauty of AI search. Then we'll go further. Jumping
a rank aspect here.
Yeah, they're ranked. So the more close you are, the closer the similarity, the first they will show. That's why the ranking is there, 0, 1, 2, 3, 4. They're ordered. Fun, right? Jumping dog. Oh, how many of you would agree that this shows jumping dog? Imagine a machine that understands that. By the way, no captions were given. You can't say that, no. It was just reading the caption. No captions at all. Right? Then
Can we confuse it by having a dog that is not jumping and just caption it with a jumping dog?
in this particular model, there is no place to give captions. So pathway through the forest, it comes up with this. Actually, I was surprised because it took me a while to see this item number 4 here, blue, snowed, to realize that it's actually pathway through a forest. For me, it took a while to realize that, but the machine knows it. Right? So you can pick up, there's a bit of homework that you guys can play with. Car, the pictures of cars here are somewhat mediocre.
So
One person
what kind of machine do you need to?
Laptop is fine. I deliberately, this entire code base that I've done, I've deliberately designed it in such a way that the humblest laptop will run it. Right? That's why.
CPU, CPU,
Perfectly fine. It'll run a bit slower. You might need a little coffee sipping along the way, but it'll work. No. I've deliberately used things so that it runs on everybody's machine. That's the thing. Now, in a previous batch, actually, last time I was giving this course was in June. So somebody said, what if I gave a word like serenity to search for? So I'll let you decide whether these pictures are reflective of serenity. And the language model understands serenity visually and the meaning of the word. Is it impressive, guys?
Yeah.
Right. But this is only the retriever part of the RAG. Would you like to now go to the generator part of the RAG too? Right.
One question: how big is a clip model, for example, in terms of parameters?
These are very tiny. By today's standards, where everything weighs in billions, these are puny drops in the bucket.
200,000 parameters. And what kind of hard disk space when you downloaded this model?
25K. I think it comes to about. It needs a few gigs. I think 1 gig or not 1 gig. Yeah, 1 gig, maybe. I can check it out.
1 gig for the whole model.
No, not for the model, for those images.
No, I'm asking about the model itself.
Oh, the model itself is puny.
Very puny.
Yeah. They're very small. See, whatever the number of parameters is, like think basically that many gigs in the order of either twice that many gigs or 4 times that many gigs, based on precision. If it is full precision, is 4 times. If it is, so it's 100 million parameter model, right? 100 MB times 400 MB. Puny, right? These are nothing.
Is there a training involved to make the model to understand?
Oh yeah. So we haven't done the training. You're downloading pre-trained models, right? How to train the model is, of course, a longer journey. For that, you should register for the class.
So this model is similar to like any other models you would download.
Yeah, exactly. Yes. So guys, this was just the retriever system. Now I'll show you RAG. So see, when people talk of RAG, there are 2 ways of doing RAG. So I'll do, people see, and this is a point I want to make. Did I ever make the statement that RAG is deceptively simple? People say it's easy. I go to this open source project, 4 lengths. Hey, I learned RAG today. I can do RAG. Let me add it to my LinkedIn profile. Right? RAG expert. So what's the problem with that? There is actually a problem. So I will do a simple RAG. And by the way, I took an adaptation from one of the leading open source projects, Llama Index, which does it very well. But to get you started, it gives a simple example. So we'll go over this code, and I apologize to those of you who don't know Python, but I'll explain it to you. Everything starts with line 22. What it says is simple directory reader, means in some directory are some documents. I will read those and make them into vectors. Right? So you just point it to the directory. Let's go and see what does that directory contain. It must contain something. Data. Data has a starter directory. There is Greek world. It's a Greek world, a study of history and culture. That sounds rather ponderous, right? It's all about Greek. We'll let it be. We'll go back to basic RAG. So now we know what is there. By the way, when I said the corpus has gazillions of documents, my definition of gazillion, for the sake of, because I wanted to create a small project for you guys, gazillion amounts to one, right? So, right. So we'll search into this doc. What does it do? Next line, 23, what does it do? Vector store index from document. Vector store means all the vector fam that you extract from it, you index it, you keep it somewhere, right? From where? From that document. So what are you doing? Can you guess what this line of code is doing? It's taking the document. Actually, it's doing a little bit of breaking up also. But out of that, it is producing vectors. That is it. After that, you're saying, okay, now that you've created vectors, you behave like a search engine, which makes common sense. Means if I give you a query, convert it to a vector, go and find the nearest neighbors. Does that make sense, guys? Yeah. Everything that we discussed a little while ago. So query engine, you put it in a search mode, and then you say, what are some key features of, this was Greek civilization, right? Greek civilization. Make sense? Suppose I were to run this code. Let's see, something should happen. And here you have to wait because it's a rather ponderous document with hundreds of pages, right? So it is working on it. And it will come back. And it's a very simple question. What are some of the key features of ancient Greek civilization? You can pose your own question, guys, about Greek civilization and culture. And when you get this code base and you play with it, so it will come up with an answer. So it says some key features of ancient Greek civilization include their architectural sophistication, right? If you have been to Athens, how many of you have been there? Parthenon? Seen the Parthenon? Would you agree? It's wonderful. Okay. The development of tragedy and drama, the Greek tragedies, of course. Their intellectual intelligence and self-criticism, the existence of blah, blah, blah. So we'll assume that it's correct from the document. So what just happened? Search results were fed into a language model, which in this particular case, OpenAI, it was kept it simple, which converted that to an answer, isn't it? Understood the language modeling, language understanding capabilities of the language model. The generator kicked in and it manufactured an answered version.
Could you show the search results here before we answer this?
In this simple case, no, but later on we will. I'll follow through in a little bit. But I kept the code simple because it's a starter code. So yay! Now let us go and update our LinkedIn resumes, LinkedIn profiles. We can do RAG.
You said OpenAI, but it's just Llama, right?
There's no OpenAI.
No. Behind it is OpenAI. Llama Index is just the name of an open source project. At one time, right, Llama became very popular because the Meta released Llama model. And then Llama this, Llama that, Olama. And so all sorts of open source projects started putting Llama in the word. Right? Yes.
You upload two duplicate documents. You don't understand. Is it going to create duplicate vectors?
Yeah, it does. It doesn't harm, but it's just a waste of space. See, in a very naive form, the way it is, yes. A better way, a good RAG pipeline will automatically deduplicate it. Right? And that's the difference between this 2-day introduction and a 3.5-month course. Right? So
which model from OpenAI did you use under the hood?
See, for that I'll have to look in my .env file, which I don't want to look into for you know why? Because it contains the key.
Right.
Right. So just let it be. Oh, so now that was basic RAG. So guys, can you tell me, this looks lovely. It worked. What could possibly go wrong? Yeah. See, all the problems that I mentioned. First problem is every time it answers my question, it loads the entire corpus. Do we need to go on creating vectors every time a user query comes? No, right? That should be a one-time operation. A common think standard Elasticsearch. Documents go in, they get indexed once and for all, right? Then queries after queries come. So indexing and querying should be not. You don't need to index at every query. That's wrong. But there's a more serious problem with this. How do you know that the answer came from the document and not from the parametric memory? Isn't it? So what I did is I changed it. What are some key features of ancient Indian civilization? There is no mention of Indian civilization in that document. Are we together? You can read the whole fact doc and you'll see there is no mention. Nevertheless, when I run it, let's see what it says. The ancient Indian civilization is known for its rich cultural heritage, blah, 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 astronomy and medicine. I could have placed the word Chinese civilization. Again, it behaves the same way, right? There is not one Chinese word or mention of the word Chinese or China in the whole document. Where did it get the answer from? Parametric memory. Remember, it's eager to answer you, right? It remembers, it knows way too much, right? So that's the problem. Why is that a problem? Let me give you a practical thing. This happens, by the way. People do RAG implementations in their workplace, enterprises, and they often use it for customer support. So these are real practical experiences early on. One hardware maker, which need not be named, but a big one, right here in Silicon Valley, deployed RAG. And they were, let me just say, they made some kind of computer hardware, networking hardware. So user was interacting with it and said, yeah, I'm having this problem. And do you know of any product that fixes it? RAG looked into this. It couldn't find any product that had that specs, that much power. So forth. And it very helpfully suggested all the competitor products that had that feature. Right? Now, most Scrum enterprises wouldn't want that, isn't it? So what do you need? You need guardrails. Don't. Even if you know what companies want to make money, they don't want to lose a customer and funnel them to the competitor. You see the practical problems, isn't it, guys? So therefore, you lose the safeguard. It is answered, even though you can count that the search result didn't have the answer, right? You can verify that by going to the doc and searching for the word Indian or China, and you don't find a single mention. That is, and I can go on. I can spend from now till midnight recounting to you the problems that are there with basic RAG, right? So we'll leave that. So we need to build a RAG pipeline slowly. So how do you grow? It's like growing a baby, right? You have to. It takes many years. Right? So before you can unleash that child onto the world. So how do we do that? What we'll do in this is we will go and into the search. There is semantic search. Right? We have already talked about semantic search. So let me bring in some concepts now. Where do you store the vectors? In the first example, we kept it in memory, isn't it? But you don't want to keep it in memory. Why? Partly because you'll exhaust the memory. But there's a more practical problem. See, suppose you have a query. Even when you convert it to a vector, if you have 100 billion documents, by the way, a web scale company, 100 billion is a small number, right? Images, documents, whatnot, and you want to search against that. What will it mean? If you keep it in a list, you have to do a linear search for the k nearest neighbors, isn't it, guys? And so means if the size of your corpus is n, you'll have to do order n cost per search, per query. Even with dot products being cheap, cosines being cheap, nevertheless, it's very expensive because the size of the cost per query scales with the size of the corpus. You need to do better to find the k nearest neighbors. And so it turns out that this problem actually antedates all of this. People have known about this problem with vectors, and they have been specific, what today we call vector databases or vector indices, which use smarter ways to find the nearest neighbors. They are all, they lose a little bit of accuracy to gain a lot of speed. So one easy way to tell you about that is, see guys, when you want to paint your wall, what happens? You will carry a card, or with your cell phone, you would have taken a picture of the wall, isn't it? And you go to the nearest hardware store or paint shop, and you see a whole palette of cards there. Instinctively, do you do a linear search and compare it to all of them? Or do you zone into, like, this is cream colored, here are all the cream colored cards, and this is green colored, and here mine is green. You zone in. So you first do a hierarchical bucketization, isn't it? You know where all the cream colored ones are, right? And because your wall is cream colored, you zone to that, and then in the neighborhood you find the right one. Did we do that? So did we have to do linear search? We didn't have to do that. We did a much more efficient thing. Right? Pretty much that is what vector databases do. They use clever techniques to not do order n search, but far more optimal search. How much more optimal search? Here is a metric. Algorithms like HNSW and for example, one of the open source projects is FASS, released by Facebook, right? FAISS. What could it possibly mean? F for AI for AI. Search. SS is a giveaway, right? Semantic search. Right. So you can do that. And these very industrial, very rugged algorithms. And then there are, of course, commercial products like Qdrent and so forth, and different ones, Melvius, etc., that scale really well. Qdrent is just amazing. I love that. What happens is they can do against a massive corpus of images and documents. They can get the search from the vector database. They can get the response, k nearest neighbor, documents, top 10 documents, for example, in how many seconds? If I give you, let's say, a few billion documents, how many seconds would it take to return the top k results, top 10 results, let's say?
1 minute.
1 minute? How many milliseconds? Milliseconds. Oh, how many milliseconds? Anyone else's guess? Imagine writing a SQL query against 10 billion or 100 billion document rows. How long does it take? Well, depending on the indexing strategy, but it will still take some time, isn't it? But you realize the vector databases are so optimized. And I can give you a fact from one of the web scale companies, because I happen to know. They literally would consider it a fault that needs investigation if at runtime the query response time exceeds a budget of 40 milliseconds. Right? And for modest size enterprise document, we are talking of web scale companies, global web scale companies. But for your enterprise, your document corpus typically will return in 2, 3, 4 milliseconds. So you were right. But I had to misguide you. Okay, so there we go.
Is it by virtue of some caching strategies, augmented
No,
caching?
it's mathematical structure.
Is it manual?
Pure math. It's really amazing, actually. So I'm saying that, see, there are two ways of looking at our field, guys. One is from the lens of practicality. Hey, I need to do this project and we need to do some RAG. Right? Another is actually underneath it all. I hope what I'm trying to create is a sense of appreciation of what beautiful machinery, right, and concepts underlie this whole field. It's just absolutely amazing. And once you get to see that the beauty, you just get very fascinating. Okay, what have we as humanity cooked up? It's just wonderful. So anyway, this code base, I can So what happens is that I tend to write code. By the way, when you get this code, you'll notice that I tend to write very idiomatic code, which is like I write in object-oriented way, classes and objects, etc. So for those of you who are beginners in Python, may come as a little bit of a stretch, but it's very design patterns based, single responsibility pattern. Very. So here is this thing called semantic search. It will just search, but actually I'll ignore that. Why don't we just go straight to animals? There's a class called animals. Let's look at the outline of this class. Outline of this. So when this animals is a full RAG system, when you start reading the codes, just read this one file, animals. Right? What does it do? Given a corpus of documents, it will load it and vectorize it, put it into a vector database. In this particular case, I use QDrint because we like QDrint. This is an embedded QDrint, this is local QDrint. You don't have to download and install anything. Right? When you get this project from GitHub, it will sort of work out of the way. So load and index. What will the load and index do? As you can imagine, it will take the corpus of documents and it will do this. So where is the corpus? Let's go look at the corpus. Oh, there is the little corpus. For the sake, just so that it runs on your laptop, I have a ginormous corpus of 100, not million documents. Right? Just 100 pieces of text. These are actually quotes about animals. And by now, you'll be sick of the fact that I love animals. Right? So these are all animal codes and animalism codes. So there you go. So this is our corpus. With this corpus, what do we want to do? Each line, each text is in a JSON-L format, means each text is one line. It gets converted into an embedding vector. We need to do that. Load and index method, therefore, does what? Load and index method, where do that? Let me remove that. Animals. This is the thing. And the animals class is, where is it? We'll go back to animals. Load and index, load all codes, vectorize them, load from JSON, etc., etc. As you know, all of these methods are helper methods. At the end of it, they will make vectors out of it. Those vectors need to be stored somewhere in a good index QDrint, a vector database, right? Because they will avoid you a linear search. They'll do very efficient mining. And by the way, they're full blown. What happens is that while you are querying, new documents are making their way into the system. They take care of all of that. Their scale, sharding, everything is taken care of. So obviously, like every database, I come from Oracle background, so you can imagine that enterprise class databases have a lot more going under the cover. But in simple terms, that's what a vector database is. Just use it. Then when you search, when you look at this code, guys, I must mention that when you see all these requires and ensures, imagine it doesn't exist in code. I erase it out. I write very strict code, which means that, for example, if the query term is missing, then what's there to search? Right? Empty query, etc. So this is it. Let me remove this. And what it does is it searches. Let's go through the search thing. Search limit is up to, if you don't specify a search limit, it will assume 3. Initial search results, it will go and set the threshold, right? Set search with text, it will apply. And then it will apply some metadata filters if needed. Yeah. Filter by author, by category. Final results, it will give you this. That is it. Right? It will give you the search results. And then what do? When you do the overall method is RAG, the full RAG. What will the RAG do? RAG is made up of 2 phases, isn't it? Search and generate. Right? So let's see if the method looks like that in the code. I apologize that this code is a bit more formal. So step 1, perform the semantic search. Just read the comments here. Does it look self-describing, the code? Right? And then step 2 is generate the RAG context. After that, right? because you have to take the query and the search results and give it to the LLM as the input. So you have to prepare the input, isn't it? How do we prepare the input? What's the prompt? Here is the prompt. So let's read this entertaining prompt, because LLM doesn't know that you're feeding it the search results, isn't it? So you tell the LLM, you are an expert assistant specializing in animal wisdom and quotes, right? You have access to a curated collection of meaningful quotes about animals, etc. This is your base knowledge, author, category, etc. Your capabilities, answer questions, provide citations, etc. Response guidelines. So this is basic prompt engineering. You give guidelines, right? Be conversational, use quotes effectively. But one of the things, by the way, in RAG that people miss, I think one of you asked this question. When you get a response, how do I trust that response, that it's actually coming from the search results? So isn't it a good courtesy that every statement that is made is grounded in or gives reference to the search result, right? And this is one of the technologies you learn here, that never just produce an answer, produce a complex structure in which you give the search results. You not only give the search results, what we recommend is you give the highlight, because there may be too many search results. You give the key highlights of the search results, and then the answer, and then a few leading questions. Because what does ChatGPT do? Or Perplexity do? Or Cloud do? You ask it a question, at the tail end, what does it do? It anticipates the next question, right? It is important to do that. And also to remember the context. Who are you talking to? So the next time you come, the conversation that you have had so far should be the context of the next question, right? So this is it. Good. And you basically tell it example response, a structure, similarity score, usage, and you tell it that you will be given that. So now you see it's just prompt engineering, isn't it? Structure, top K results, query, it ships out to the LLM response. That's the generator part of it.
I have a question. I've read somewhere, when you do the prompt, you can say, don't hallucinate. Does it add any value?
See, you invariably do that in good RAG. See, I tell you, I put lots of, let's say that you're a kid, right? And I put lots of candies in front of you. And then I leave the room and say, don't eat it, right? What's likely to happen? Right? You have LLM is a kid that's over eager to answer. Telling it not to hallucinate is no guarantee it won't hallucinate, isn't it? How would it know? Think about it this way. Okay, can I give you a more mathematical answer to this? It's a bit technical, I apologize. See, what happens is that the tokens that get produced, ultimately LLM is producing one token at a time. Understanding the patterns and structure of human language, whenever you feed something in, it has a probability distribution over the vocabulary. On that vocabulary, you're sampling a word, sampling for that to pick a word, right? That is nuclear sampling or subsampling. You're not necessarily picking in the most probable word. So first of all, stochasticity is introduced right in the sampling itself, right? Now what happens is the shape of the probability distribution, intuitively, the machine is putting mass on some words, the probability mass. Imagine, think of it as sand. It's piling up sand on this word and this word, so that when you sample, they are more likely to show up. What happens is that when it is not sure, right, the way it shows up, so suppose all the words have equal probability, nearly equal, right? It is a sign that the machine is not confident what to say. Nevertheless, the machine will not stop till it happens to produce the token end. So you're sampling off a underconfident machine. What will you get?
But isn't there like a temperature or something?
Temperature just says make the mountains higher. The sand hills for high probability words higher by modulating that. Yeah, modulating the height. Like, you're making, by increasing the temperature, you're shrinking Mount Everest's height so that the nearby, your Mount Diablo begins to compete with Mount Everest. Right? That's all it is doing. So let's say Mount Diablo represents the token Diablo and Everest represents the token Everest. Right? If the two become little bit more comparable in height, when you randomly sample, you might end up saying Diablo. Yeah, that's what temperature does. See, understanding, and this again goes to the RAG course itself, we go into all that mathematics very carefully to understand what does temperature mean. See, the word temperature, when Jeffrey Hinton introduced temperature into the softmax equation and so forth, and all of this, I mean, it's a long history. It comes from statistical mechanics in theory, in physics. It actually comes from Boltzmann equation, right, and the study of ensembles and so forth. Not to spare you, but in this detailed course, we do a lot of very engineering practical implications, but I don't spare you that other consideration also. So I'll take you through, so you understand what all of these things mean. But at the end of it, the one thing that you will learn is just saying do not hallucinate does nothing. Right?
Instead of saying do not hallucinate, you could say though that if you don't find it in your in the document, then do not come
It
back
is not
with
a
an
guarantee.
answer and
Yeah, it's not a guarantee. In other words, it takes you forward a little bit, Varsha. It helps a little bit. But see, would you cross a road if there was 20% chance that you'll be hit? Right? You wouldn't, right? You need a method that is sure shot that the machine has not hallucinated. There is such a method. Right? We can do that so that you mitigate the chance of hallucination to vanishingly small amount. Rarely does it ever happen. Right? I mean, see, every time you cross a road, there's a chance you can be hit. Nevertheless, you do cross the road. You look left, you look right, and you say it's safe, I'll cross the road. You need to make it safe like that. And there is a way in the RAG course, you will actually we'll learn grounding, how to ground every assertion of the result back into the search results, which is exactly what I was saying, and I'll show that to you. Your question.
So I recently had a example where I was doing real estate comparables to show a client. I actually fed a spreadsheet which showed 4 actives and 3 expired or cancelled, meaning the properties that did not sell.
Yeah.
So 4 plus 3, 7. And in a explanation, it somehow got 2 20s. And
Oh.
I said, "Are you hallucinating?" And it says, "No, I'm not hallucinating. I actually misread your data where it said 4 actives and 3 expireds, and I thought 2 of them. I did not go that far to that column to understand that it was not 4 active.
It's rationalizing.
It's yeah. So I didn't quite understand what that meant. I mean, I thought it brought data out from somewhere which was not existing in the table itself.
Yeah.
And it still says that, oh, I was not listening.
Yeah. So guys, can I just show all of this in an example? There must be test examples. Where is the examples directory gone? Yeah. Simple RAG usage. So one of the points that I'll just run this because we are running out of time, guys. But see, guys, have you seen Perplexity or ChatGPT or Anthropic? Do you notice that they rarely ever hallucinate? And they give you very structured responses. They give you references to everything. That is the benchmark. Unfortunately, people don't build systems to that benchmark. I will just show you this thing. I asked, and this code is with you. I asked it this question. What is the question that we asked in the code? Let's go and ask this question. Just to show you, this is an example. Simple RAG search. Go through this example. Unfortunately, because I've increased. The query is on line 39. What do animals teach us about love? Right? So then it goes through this codes, it produces it. But the point that I want to make is, here is how you really want your response First thing it says in the response as a structure, see, you may not show it to the user, but it should be there for you to gain confidence. LLM answer to key insights. It went through the results. First of all, it has an answer. Animals can teach us profound lessons about love through behavior and nature. John D. Found 3 relevant quotes, right? Key insights. Animals, it comes up with key insights, right? Animals, etc. Do you see the key insights? Animals express love, blah, blah, blah. Recommended quotes, right? So it is telling you which of the documents, right? See, remember, a RAG is also a search engine. What does a good search engine do? Show you the search result, right? So it is doing that. And then it is giving you follow-up questions. So I'm just giving you a sense of why would I trust this answer, like your question, right? Why would I trust this? When you give the sources, and not only give the sources, you summarize the search results themselves separately from the answers. You see how much value you bring, right? And then you give leading questions, follow-up questions, right? So all of these, how about we do it on Wednesday? I know that many of you are packing your stuff. So guys, I'll conclude. I'll take questions. And before I take questions, I'd like to thank all of you to come here to support Vectors. We are an AI training organization. You got a taste of that training. So there's lots of animals in the RAG course, right? Right. But more practically speaking, you will create enterprise class, real RAG systems. Next time when you come, I will talk about what a real RAG system implies. What should it have? Right. It's far more complex than you think. Right. As I said, it looks deceptively simple. It is one reason most enterprises don't get it right. So I would like to end with a quote and a story. So there was an author named Leo Tolstoy, most of you know, who wrote the book Anna Karenina. Right? He wrote it when he was on his honeymoon. He had married a sweetheart and he was on his honeymoon. And then he sits and writes this book on his honeymoon, which is one of the most depressing commentaries on marriage. It starts with the famous statement, all happy families are alike. Each unhappy family is unhappy in its own unique way. So I would like to paraphrase it by saying, all good implementations of RAG are alike. Right? There are very few, you can count them. Each enterprise RAG implementation is unhappy in its own unique way. The reason for that is most people prematurely think they know how to do RAG. And what they do is they end up making a half-baked product. There's a difference between doing something to perfection and doing it well and scalable and high performance that people can actually trust rather than something that's just a proof of concept that will impress your leadership, but actually at the end of the day will not work out. Just this week, a study came, MIT says 95% of AI projects fail. Actually, of Gen AI, RAG is the poster child. Agentic RAG is the poster child. Okay? And you can quite imagine that it's failing because most of the AI engineers doing it, they think they know it. They don't know that they don't know. And I hope I have inculcated some sense of appreciation for the beauty of the subject. It's really an amazing subject in its own right, despite, whether or not it has practical applications, I would like to say, and it has tremendous practical applications. All right, guys, I'm going to end the Zoom session.